let's take a closer look at the product and quotient rules of differentiation. The objective is to implement the product and quotient rules to find a new derivative function. Before we begin, you might want to do this warm-up problem to help you realize that the product rule is not as obvious as you would like it to be. It doesn't have an obvious computation. And so here's one way to see that the product rule will not have an obvious computation. You might want to consider performing this warm-up and try to investigate, try to figure out the patterns here, and answer this question here. Is the pattern given in this equation true or false? And I gave you a hint here by looking at a couple of simple polynomials. Now, what is a counterexample? A counterexample is an example that will actually disprove a following statement. So usually when we write an equation, the hopes is that this expression is going to have the same value as the expression on the right. If you're still struggling to provide this counterexample, you could actually follow along. Now, if the obvious pattern for a product derivative is not true, what could give you some intuition of the derivative of a product function? Here's a particular example that involves running speed. Let's say there are two characteristics of running speed. There's stride length and stride rate. But what if there is a change in stride length and there's a change in stride rate? You might think you could look at each change at the same time, but it turns out you don't want to look at each change at the same time. You want to look at each change individually. So the goal here is to realize, okay, if the stride length changes, how will it affect your rate of change with regards of the stride length? So this example will go into great detail of that. So how does the stride length provide a change in speed? So you could keep the same stride rate, which is 2 strides per second, but your stride length actually now has increased by half a foot. So you calculate this individually and you'll get the change in speed relative to the stride length. You do a similar process where, what if your stride rate changes? Let's say your stride rate increases by 1/4 of a stride per second. Then you calculate that change in speed relative to the stride rate. Notice that will increase your speed as well. The total increase is the sum of these two numbers, And if we write that total change in running speed, we'll see a pattern like this. There's a change in stride length, and then you multiply by the original stride rate. There's a change in stride rate, and then you could multiply by the original stride length. And if you add these two changes together, notice you get the total rate of change. So this gives you an intuition of what a product of two functions and their rate of change would look like. It'll give you a pattern where there is a sum involved. The derivative of the quotient of two functions is not obvious either. And here they are. Here are the product and quotient rules together. The first two is just different ways of writing the product rule. You are responsible for knowing both because we do need Leibniz notation and we do need prime notation to indicate functions. Leibniz notation is more important, so make sure you're able to write the Leibniz notation. Now the goal here is just to take derivatives. You might need to use a lot of scratch paper or just to help yourself organize your work. If you need to, you could look at the product function here called h of x. You need to see it as a product of two functions, so you might be able to specify exactly what they are, f of x and g of x. However, I'm actually just going to take the derivative here because I have actually memorized these computational tools already. I strongly advise you to memorize the vocabulary and the language before you try to proceed with your practice. That way you don't have to look it up over and over again. So to illustrate the derivative of h with respect to x here, I will go ahead and highlight when a derivative takes place. So there is a derivative, and notice the other function stays the same. And that finishes the product rule. However, your algebra says, you know what, take out the greatest common factor. I'm going to take out a half, an e to the x, and I'm going to take out an x to the negative 1/2. And then write the other factor, which is 1 plus x. Now this technique in algebra turns out to be very important as we're going to study another topic that involves critical numbers. So if you can factor like you did in algebra, you'll learn how to write things much easier later on. And so there's the derivative. Notice the domain just changed slightly compared to the original function. The original function's domain is right there.